First of all, I'd like to congratulate the CCP-EM team for organizing this, what I suspect may be the biggest cryo-EM meeting in Europe now. And it's so great to see so many old friends and all of you here together. So today I'll speak about new features in Relion 5. So as you may have seen on the CCP-EM emailing list, we went a public beta with Relion 5 last autumn. And there were several new features in Relion 5 and recent additions as well that I'd like to discuss with you today. Before I do so, I thought I'd bring up kind of the core Relion team. There's now many more people contributing to our code and suggestions and feature requests, etc. But these are some of the people which make major contribution. Takanori has now left the group, but he's still, as you can see on the mailing list, very much involved in feedback, and we're very grateful. Dari has now officially left my group. We'll set up his group at the Chan Zuckerberg Imaging Institute. And Johannes and Scheres are still with me. And then there's the whole team Tomo part of our group. Is Bogdan, who's here in the audience, and so is Alistair, who's now moved to Genentech. Jasenko used to work with us, but still somewhat involved. And Rangana from CCP-EM has also made contributions. So this is how the GUI of Relion looked like. And new features in Relion 5 were rethinking regularization and how to do that, work by Dari, resulting in blush regularization. Johannes worked on DynaMight for handling continuous heterogeneity in single particle analysis. Scheres introduced Model Angelo for automated model building, and then Alistair, Bogdan, and Rangana have all helped on making this full tomography pipeline, which we just put on bioRxiv this weekend. Now, because Scheres spoke at this very place here last year about Model Angelo, I will not speak about it today, just to say if you have any map that extends beyond 4 angstroms resolution, Model Angelo will now more or less build a model of similar quality as most of you would do in front of Qt. And it's actually much better than most of us are in trying to find out which proteins that you don't know are present in your lab, in your map, are actually there. And that's because computers are much better at calculating through hidden Markov models of 20-element probability vectors than you are in your brain. Okay, but I won't speak about that. Let's go to regularization. One of the main contributions of Relion was the formulation of an explicit regularized likelihood function, where we use Bayes' theorem to combine what is the likelihood of observing the data given our model with some prior knowledge about the model. And that's prior knowledge is in the absence of measuring any data. So then, of course, it becomes a relevant question. You know, what do I know about the map I'm going to reconstruct if I haven't measured any data? So the way I did that back in 2012 was just to make an explicit assumption that the map is actually smooth in real space, or that its power is limited in Fourier space, and that led to quite a beautiful kind of closed mathematical framework where you can directly optimize this regularized likelihood function. But of course, we know much more about proteins than that their density varies relatively slowly when you move from one point in real space to the next. Thanks to all your efforts and those of many crystallographers before you and NMR spectroscopists, we have accumulated a wealth of knowledge about what protein and nucleic acid structures look like. And all of this data is accumulated in the PDB and now recently also in the EMDB. Now, then the question becomes, how can I make a mathematical formula that incorporates that knowledge, and can I please also calculate derivatives or whatever I need to optimize that formula so that I can have some sort of explicit target for my reconstruction? And that is, no longer easy to just write down some mathematical formulas and solve them. So that's where we then resorted to machine learning methods. And we'd previously shown using simulated data that you can do this. You can make denoising neural networks that act within the iterative loop of Relion to incorporate prior knowledge about proteins, thereby making reconstruction better. Now, that was about 3 years ago or so. And since then, Dari has been working very hard to try and make that work for experimental data. And that's a lot harder because experimental data, there's all kinds of things we don't really know very well about some of the forward models in the experimental data. So what Dari came up with is called, he called this blush regularization. Blush because it's red, and red is regularization by denoising. It was slightly difficult to get to the name, but that's what he decided. And it's based on a noise-to-noise type of training of a neural network that we have trained on many different EMDB half maps. So this neural network has kind of learned something about signal in and noise in EMDB maps. And importantly, there is no atomic models like PDB. There's no information from the PDB going in. This network has only been trained on half maps from the EMDB. Dari has implemented several quite clever tricks on how you can then let that network also focus on what to do with membrane patches and solvent regions, etc. And then what he comes up with is a neural network that just takes a map as an input. And if you run the network, then it brings out a denoise network. Now, here in panel D, for example, this is a slice through a 3D reconstruction somewhere in the middle of Relion refinement or so. And if you put it once through this network, this is what comes out. So you can see that little speckles in the noise will be smoothed out, and the membrane patch have been nicely smoothed out. The protein density is mostly intact. Perhaps it's sharpened up a little bit, but quite conservatively. And overall, the change is relatively minor. But by putting this inside the iterative refinement of Relion, so every iteration we do this, we gradually steer the refinement, kind of incorporating the prior knowledge that we hope is embedded in this neural network inside of the reconstruction algorithm. And that, if you do over multiple iterations, can have quite big effects. So this, for example, I will show it in more detail later, is in amyloid. And this is if you would use normal conventional refinement in Relion 4, you would get all these kind of artifacts in the solvent. Many people of you may have seen these, we call them sunshine rays coming out of maps. If you look at them in slices, these are overfitting artifacts as the signals are too weak. Now, Blush is particularly good at removing those and thereby steering the refinement in the right way. So if you do this for 25 iterations or so, then you can get to a map that looks like this. So we tested this on several data sets. PFCRT is quite a common one that has been used by multiple groups. I think the Structura team used it for non-uniform refinement, and Chris used it for, how's it called, side splitter. So we thought we would use this too. This happens in conventional refinement and then local resolution colored in Blush. And then we now think, how good is your map? Not just resolution is a metric, but how well can I build a model in that? That used to be a subjective kind of task, but now we use ModelAngelo to model that, and you can see that also the amount of model that gets built by ModelAngelo increases quite a lot, and that agrees with all the FSC curves. This is a GPCR dimer from the Tate lab at the LMB. Normal standard Relion 4 refinement gives kind of blobby helices, and you get stuck. And then you do get to much better helices with some sidechain densities and a correspondingly more complete model in ModelAngelo if you just switch on blush regularization, which is just a little tick on the GUI now. Now, because it's especially good at making overfitted refinements better, that's when the signal to noise ratio is small, and that happens if you have small complexes. I'll show you an example in a minute. But also if you have large complexes where there is motions in between the different domains, then you can separate them up in individual independently refined bodies in what we call multi-body refinement in Relion. And there, if you would choose your bodies too small, you would again run into the problem of overfitting. And you can also switch this on, this blush regularization and multi-body refinement. And this is our normal multi-body refinement of this spliceosome data set, and this is after blush. And again, ModelAngelo models get much more complete, FSCs improve, etc. This is the amyloids that I showed you. This is a first intermediate amyloid, or the FIA, which was solved by FIA in our lab. She named it after herself. And this is in standard Relion 4, and the same refinement in Relion 5 basically solves the structure. Now, I told you it's particularly good at doing small molecules and also small complexes, I mean. And so this is ACA2. It's a 40 kilodalton protein nucleic acid complex, which Max Wilkinson, who used to be in Kiyoshi Nagai's group in the lab, who's now in Boston. This is a project from his time in New Zealand. He was unable to solve this for about half a year or so using CryoSpark or Relion. He was completely stuck. And then he sent the data to Dari, said perhaps you can do something with it with Blush. Dari went through a relatively straightforward procedure where you use Blush both in 3D classification and in refinement, came up with in the end with a 2.6 or 7 angstrom map, which we used Model Angelo to automatically build most of the model. We sent this to Max, only the map, because we knew Max really loves model building, so we kept the model at home. Okay. So Blush, if you haven't used it yet and you have difficult refinements, do give it a go. It has made a major change to many projects in our labs, and I also hear from many of you in your labs. DynaMight is the development by Johannes Schwab, and it stands for Modeling Structural Dynamics that might improve your map. Now, DynaMight is based on a variational autoencoder type of structure. Alan will later also speak about CryoDragon. I think she was the first to kind of introduce this type of structures for handling continuous heterogeneity in the field. We use a kind of method which is also closely related to Muyuan Chen's method from Steve Lutke's lab, which is because we place multiple Gaussians in real space, and the decoder of our VAE predicts displacements of these Gaussians, which are kind of pseudo-atomic models of our density, and then we make projections of the displayed Gaussian with the forward model and try and minimize the loss, comparing these to the experimental images. New to our approach is how we regularize these Gaussians, and I'll come back to that. Plus, we now also divide this separately into two halves of the data. So we independently refine two completely separate VAEs because of keeping things gold standard, and I'll also come back to that. Now, this then allows you to make movies of wobbling things like you've all seen, and Alan introduced some of these with her methods too. Now, Johannes went then one step further, and he said, okay, now that I know for every particle which pseudoatoms move in which direction, I can try and undo those motions and try and make a better reconstruction of what we call the consensus model. So it's not entirely clear biologically what the consensus model is. It's some sort of average where we try and undo all these motions that actually exist in the data. And because we do that we do in real space with a default back projection algorithms where you back project not in straight lines, but now these lines kind of warp around according to the displacements. You then can, because we do all of this gold standard, you get two independently refined half maps, which you can calculate truly gold standard FSCs and see if you made things better or not. Now, this is, again, a spliceosome example, and this is the consensus refinement in Relion. So you can see the top here wobbles around a bit. Here, what we call the foot also wobbles around. If you do the VAE with completely no regularization on the Gaussian, so every Gaussian can walk in whatever direction it wants, then again, we have a highly ill-posed system where overfitting, etc., goes out of hand, and you actually make things worse. So you need to tell Gaussians, you have to kind of walk together if you're close to each other, etc. If you do that using an atomic model and you more or less impose the structure of the atomic model to some, with some restraints, then you get very nice high resolution improved reconstructions in DynaMight. If you take a slightly less agnostic approach where you don't use an atomic model, you just build a map randomly with Gaussians and then keep neighboring Gaussians close together, moving in the same direction, then you get this solution. So you might say, okay, put in your atomic model, go for it, and you get this map. So, but of course, then we have to be careful. This field has suffered majorly from Einstein from noise artifacts where, you put your will onto the data. You use a reference and then you align your data to it. There's a lot of scope in overfitting the data, and kind of model bias can have a very bad effect. And we showed actually, so Johannes did some controls where we put the right model in a very floppy part of the spliceosome, or the wrong model in, so deliberately a wrong model. You can actually generate density of the wrong model very beautifully in the most floppy parts of this structure. And you wouldn't, based on FSCs, that would all still make sense, but you're now doing Einstein from noise. So there's enough parameters in your VAE network, just like there's enough parameters in all the rotation and translations in the conventional alignment kind of Einstein from noise to actually invent things. So if we're going to do, and I don't think what we're saying will not be the last word on this, because this is prior knowledge. We know sometimes what the structure is, and we should be able to use it, but you have to be careful, and you have to check that you're not inventing things, because it could go wrong. And we also showed, if it's a slightly less floppy bit, then this effect becomes less important, but it's still there. So there is also a continuum of where there is scope for this overfitting and not. But based on these observations, now what's only implemented on the GUI is this approach. So we're sacrificing a little bit of resolution perhaps, but at least it's safe. You won't be inventing wrong things. Now, some applications. This is a complex from the David Barfoot lab. It's part of the yeast kinetic core, a CCAN with a SEMP-A nucleosome. This is the consensus refinement structure if you don't do anything about heterogeneity in Relion 4. And you can see, the nucleosome itself, local resolutions are quite low, and here at the edges as well. If you now do DynaMight, you will get a latent space, and you can look at different points in latent space, much like Alan has shown us with Cryo Dragon. You can make maps, and here is 4 different maps overlaid here on the red one. So you can see there's different motions, and you can make a movie, which I'll show in the next slide, of how this just walking around latent space. If you now do the improved reconstruction with the deformed back projection, then you get this local resolution map. So look at for example, here about the DNA around the nucleosome, and you'll see that all the local resolutions have improved quite dramatically. So you can make much better maps using DynaMight. And this is just now a movie of different maps as we walk along latent space. Okay, but you could make a movie of this in any case, but you wouldn't. Are these rotations that you see of these domains actually happening on the data, or is it some sort of overfitting? At least that the map has become better resolution using these type of motions is an indication that some of this is probably real. Now, we've done the same. This is a similar, it's almost twice as big, with the SEMP-A, and now 2 copies of the CCAN complex. Another data set with similar kind of behaviors. And this is now the improved map from DynaMight compared to the Relion consensus map. Now, this complex is big enough that Tom Dendove in David Barfoot's lab could also do multi-body refinement, and he split this complex up in 4 bodies. And this is the map colored, the kind of composite map from multi-body refinement colored by local resolution. So DynaMight is not yet as good as multi-body refinement. So if you can split things up, and perhaps with Blush make that better, then that's still better. And we're trying to understand why that is. There's much more constraints, of course, on motions here, and we're now trying to develop DynaMight into a direction where we do some sort of multi-body refinement that starts approaching this without you having to define any bodies. That's for the future. Now, we sent this all off, and then, when I write papers, I hate comparisons of myself with other people's software, because I see many people comparing their software with my software, and I always think, oh, you haven't used my software right. So I try to shy away from this. And my first paper did not have any comparison, but then the review said, oh, you have to compare it. So anyway, they suggested we compared with 3D Flex from CryoSpark. So we had never run CryoSpark. So we installed CryoSpark. We're not good at CryoSpark, but we just used the default parameters on the GUI and the same number of latent space dimensions as we would use in DynaMight. And this is the result colored by local resolution as estimated in Relion for both maps from the half maps that were generated by the 2 programs. So you can see that the local resolution estimates in the 3D Flex map are considerably better than those in the DynaMight map. However, if you now look at the actual densities, you start to see what that actually means. This nucleosome has quite good local resolution, but there is no major and minor groups, whereas I have much lower local resolution, but I can clearly see features. alpha helices that should be separated are not separated. What we think is happening, because we're using completely gold standard separation of our two VAEs, we actually get realistic estimates. And actually, I think our map is not only, are our estimates of local resolution better than those in the 3D flex map? Also, the actual quality of the map is better because you'll be able to build better models in this map than in that one. So, but of course you can say, you don't know how to use CryoSpark, and I will be the very first one to admit this. So what we also did for the reviewer is to then just download one of the data sets that the 3D Flex paper included, and this is Empire 10073, another Spliceome data set from the Nagar lab. And we tried to run it DynaMight on that again, and then we try to use it here. We use CryoSpark to do the local resolution estimate, because that's what the 3D Flex paper also used, and we get better local resolution estimates than the one in the 3D Flex. But yeah, as I say, I'm not a fan of these kind of comparisons because I think they can be gamed. Okay. Now the last bit is a new tomography pipeline in Relion 5. Now, when I wrote the email of the beta release back in autumn, I said, that's not ready yet, don't use it. Some of you I know have been naughty and have been using it, but and I'm grateful for those of you who have provided feedback, which have helped to make it better. But as we just announced this week, that has now been finished, thanks to a lot of work from the people I already mentioned. And I'll briefly walk through it. You can now, provided you install version beta 3, 5.0 beta 3, and you type Relion -- tomo, you get a specific GUI that looks just like the one for single particle, but is now geared towards tomography. So we start with the import, and these are raw movie frames from your microscope in ER or TIFF or MRCS or whatever, and the MDoc files, that's Relion or this Thermo Fisher software right out. We then run motion correction in Relion, CTF estimation through a wrapper to CTF find 4. Alistair Bird has written various Napari-based visualization tools where you can then see which tilt images get a gold bar in or whatever, and you can chuck them out. We then align tilt series through wrappers to iMod or RTOMO. Not yet, RTOMO 3 is the latest, I think. That's on our list to do. We reconstruct tomograms in Relion. We then provide wrappers to do denoising in CryoCare from Florian Gug. And then we use again, Napari-based viewers from Alistair to do particle picking. And that then brings you straight into the Relion 4 type of subtomogram averaging pipeline, but now using the entire Relion pipeline with star files at each stage of the process that define each of the metadata formats that you need to do the next stage. And so the way into what used to be Relion 4 subtomogram averaging is a lot easier than it used to be, you know, depending on all kind of Python script to iMod, and it depends which version, etc. All of that hopefully will be better now. And another change we made to this part is that Relion Refine can now work with 2D particle stacks rather than what we call 3D pseudo subtomograms in Relion 4, which makes it about an order of magnitude faster and lighter on your disk. So you'll be happy to hear. So these are just some screenshots from Alistair's beautiful viewers in Napari. We're working, you know, this works well if you're on the same machine. It does not work so well if you use it remotely. So if you're not on the machine where you're running Napari, and we're looking at alternatives. But that's for now, this is a workable solution. So Bogdan has this poster, which is number 83, which is here up, and you can go and speak to him about it. And you'll find that there we reprocessed John Brick's 5 tomogram data set of HIV immature capsids yet again. And but in basically 48 hours from import to refine, this is running overnight with all jobs lined up, etc. But in 2 days' time, you can get to what is a 3.3 angstrom map, which is just a little bit worse than what we had before, 3.2. And that included very carefully selected subtomogram particles by Zunlong K, and whereas this just starts from individual capsids picked as spheres from which we then sample particles with equidistant grids. Good. So that's now, there's documentation for that. We have a pre-calculated results with the tutorial, just like we had with single particle data. So you can just see what exactly we did for that 5 HIV tomogram data set. And you can read all about this now on bioRxiv since this weekend. So that brings me to my conclusions. Blush regularization will make your refinements better. If you have difficult refinements and you haven't tried it yet, I would definitely encourage you. I just spoke to somebody here from Nottingham who said, oh, I couldn't solve my structure and now it's solved again. And I hear these stories every week from people. So that's, you should try it out, I think. DynaMight improves your map from data set with continuous heterogeneity. And, you know, we warn you against certain things. It's important to do this gold standard separation also if you do these neural networks, and there is scope for overfitting and model bias in these methods too. So we have to be careful moving forward. To what extent are we going to use our prior knowledge? And now we have a start-to-end tomography pipeline. You know, you start with the raw movies and you end up with the atomic model built for you in a Model Angelo, provided you get better than 4 angstroms resolution, of course. Now, the data model that we now propose in this Relion 5 tomography pipeline is a set of star files in a defined format, and you know, with angles that we take from IMOD and coordinates in angstroms from centers of tomograms, so it no longer matters how thick your tomograms are, etc. We think those could serve as a kind of a standard to speak to each other, and in that context, I think it's important to note that Doppio and the CCP-EM pipeliner also will adopt this data model for cryo-ET. That brings me to my last point, and you know, some of you have heard this from me before. I'm a strong opponent of open software accelerating science. There's a lot of commercial software in the field now, and it's very popular. I think there is a room for commercial software because there is money to do things that we can't do, like making things faster and beautiful GUIs, etc. But if you look at the field as a whole, the bulk of the scientific progress in our methods still comes from academic labs. So we have to be careful to keep a very much alive development community of academic software where we can share with each other and move the field forward. I think CCP-EM pipeliner and Doppio will play, hopefully, a crucial role in this, in providing a platform where different developers from different softwares can come together by just adhering to these 500 lines of Python code that Martin spoke about. And then if we all bring together our developments and our advances in science, we can all make science keep continuing faster. And also, if that at some point would stop and there would only be commercial software, we might end up paying for the software ideas that we initially developed ourselves. So that's all I wanted to say about that. So just to thank all the people involved, you know, Relion is now a true team effort, and I'm really grateful for all these people, collaborators on the right. And then we are looking for a new group leader if you want to join the LMB and have exciting ideas for machine learning in biology in a very general sense. Thank you very much.